Okay, let's start class. So today we will talk about the bagging examples. And this Thursday we will not have class because of the fall break. And the next week we will have one lecture on the random forest. And on Thursday I will give you an example for the using the statistics methods and machine learning algorithms on a case study. And then the week of next, we will start our midterm presentation. So I hope all of you find your group and form your group and found the data sets, and make sure you send me an email. Each group just send me one email. You can just ask one of the group members send me the email that about the data sets you are using, and whom are your teammates. So what are the who are the team members in your group, and what type of analysis you plan to uh, apply. So I will just have a quick check, so just make sure that the data sets and looks okay, and the method is applicable. Okay. So on the during the presentations, I will just randomly pick all the groups. Some of them will present on Tuesday, and some of them will present on Thursday. Okay. Any questions for the midterm project? Okay. If you don't have any questions, well, let's start our bagging examples. So we will have two examples here. The first one is a classification example. This is a credit card approval example. All the attribute names and values has been changed to the meaningless symbols to protect the confidentiality of the data. And I will post this data on the Moodle right after class. So in this data, we will have 690 observations with 14 predictors. 6 of them are numeric, 8 of them are categorical. And the response is binary, is just approved or not approved. Okay, so we will try to build an ensemble model, a bagging model, using the tree here to make the predictions on the credit card approval. Okay, so this data is good as a mixture of continuous and categorical data. Okay, so let's see. This is a few lines, the first two lines, and we have these many variables, and you see we have lots of categorical variables. So these are the summary of the variables. From this summary, I noticed that you can see we have some variables have quite many levels here. Let me see what, like here the A5 has 14 levels, right? And A6 has 8 levels. So these two are the categorical variables that with quite large number of categories. As we mentioned last time, that when the categorical variable has too many categories, it can be easily leads to overfitting because we have many options to do the binary splits, right? So for these two variables, since we don't know their group meanings, it's very hard for us to merge the categories based on the meanings. Like here, we don't know these 14 categories. What does these 14 categories mean? If we know the meaning, then we can combine that, merge the groups in a meaningful way. But here we don't know. So the only way we can do is to just merge those categories with small lower frequencies as one group to make it has relatively large number of counts. So here for the A5, this is the frequency table. So you can see I highlighted 3 categories that has very few number of observations. So like the category 5, 10, and 12, right? So what I do is I just merge the 5 and the 12 to 10 so that we will have just I remove the these two just combined as one level. So here when I merged these to the category 10, okay, so you can see now the category 5 and 12 has 0 counts, so it's still there. So what you should do is you should use the drop level function to drop those levels with 0 counts, so that you will have only 12 levels, right? And these are quite balanced. Okay, this is just as an illustration. Actually, you can further merge to have fewer categories, but this as serves just as an illustration that if you have those categorical variable with many levels, maybe we can just combine some to make it fewer class. Okay. Uh, and for the A6, we have 3 levels. Oh, we have 4 levels have very low counts, so we can merge these 4 levels into one level. Okay, so I did similarly. So after merging into one, so we have these 5 categories. So I will just use this refine these 2 variables also in the data set. So I randomly split the data into training and test. And then I first fit a single tree for a single tree, and these are the variables used in the tree constructions. And here, this is the CP table for the cross-validation results. So the tree with the 4 splits give us the best cross-validation results. You can see the cross-validation error is the lowest, right? So let's just use this as the best one, but we will evaluate the other splits also in a minute. So here, I just run on the all 4. So we have basically 4 trees. This one is just a stump, has one single split. So stump means is the simplest tree that has only one split. So this is a stump. That's the simplest tree. And then this is the optimal tree with 4 splits. This is 11 splits, 12 splits. So I try these 4 subtrees, okay? And on the test set. So you can see I apply these 4 trees on the test set. And these are the misclassification error rate. And it turns out that the best tree in terms of the best performance on the test set is the first one is the stump. It has 12.5% error rate. Okay, so let's just keep that in mind. And then I will just use the bagging trees. So to do the bagging tree, how to do it just efficiently? So here I used this particular ways. So this is I use the R multi-norm. So that's is generated the multinomial distributions. Okay, so I want to create 201 trees. Each of these trees are constructed based on a bootstrap sample. Okay, so what I'm doing here is I first set the B, that's the number of trees, that's 201. And N is the number of samples in a training set. Okay, so I set the random seed so that I can exactly reproduce the results. And then I have the boot samples. That is a list of samples. And these samples are the bootstrap samples. So here the boot samples stores 201 bootstrap samples. Each bootstrap sample contains n observations, just like the training set sample size. Okay, so how to get these bootstrap samples? I used R multinorm, that function. That's the multinomial distribution with parameter is n. So B is the number of samples. So I have 201. Okay, I want to do that. So for each bootstrap sample, it contains n observations. And each observation in the original training data has that probability to be chosen. So what is rep 1 comma n? So that's a vector. It's a constant vector that has 1, 1, all the ones. So how many ones? There are n ones, right? There are n ones. And then don't forget we have divided by n. So it's not 1, it's actually 1 over n. You see that? So this is the probability for each observation was being chosen in the bootstrap sample. So that means each observation has an equal chance to be chosen, right? And that is exactly what the bootstrap sample means. Bootstrapping is sample with replacement, and each observation has an equal chance to be chosen. So that very simple, just one line code can give us all the B bootstrap samples. Each bootstrap sample contains n observations, and each observation are chosen from the training set with equal chance to be picked. Okay, so that's the boost sample. And then I have a tree. That's an object. It saves, it's a list. So the mode is a list. So this is a list. And it has B elements. And each element is what? Each element is saved a single tree. Okay? So then the pred underlying boot, this is a matrix. Okay? And the prop underlying boot, that's another matrix. And these two are a matrix with initial value, which is 0, and the n row of test data. So that's the number of observations in the test sample and the B columns. Okay, so that is the two matrix that I initialed with 0 values on this dimension of a matrix. Okay, then I started to fit first I started to have the initial tree. So I run a classification tree, y tilde dot. So y is the response on all the other variables. The data is training data. Control, I set the CP to be a very small number so that I can have a very complicated tree, okay? No cross-validation. You see X value is 0. That means I don't need cross-validation. And the maximal surrogate, no surrogating, no max compete. And if you want to know the details, you can look at the help menu. Okay, so basically what I'm saying here is that I will create a very deep tree with no pruning. There's no pruning a tree, okay? And no cross-validation. Why? Because there's no pruning. So what's the purpose of doing cross-validation? And there's no surrogate. So because the data has no missing value. No missing value, we don't need to do the surrogate. Why? Because this is an ensemble tree. It takes time to do this, to find out the surrogate variable. It takes time to manage these, to do the cross-validation. So since this is an ensemble method, we want the computation efficiency, right? So what I did here is just construct a tree without pruning because we want to have a very complicated trees. Remember we talked about that last time, is for the ensemble method, we need the tree, we need the model to be complicated, not stable model, but unstable. Unstable means that it's very complicated and try to have a small bias but high variance. Why small bias? Because if the tree is complicated, then we have a small bias. And the bagging works by reducing the variance, but cannot reducing the bias. So we need to have each tree, each model has a low bias. But the variance is high, that's okay. Why? Because we can always reduce the variance by averaging, right? So understand that, then we know that why we don't have to prune a tree, why we don't cross validation, and why not do the surrogate variable to handle the missing values, because these are takes time and useless in here. And then so that's the tree using the original training set. So how to apply to the bootstrap sample, right? The good thing is that there is a function called updates. So we can update that tree by the weights on the bootstrap samples. So that's just a shortcut in the codings and also make it very efficient to just update the tree which fits on all the sample points, or on to update the tree that constructed on the training set, but just by the updated weights based on the bootstrap samples. So that actually give us the tree, updated tree. It's essentially fitted on the bootstrap samples. Okay, so that's the tree fitted on the bootstrap samples. And then why I have these two? Because here, remember last time we talked about for the classification tree, we have two ways to average. One way is to average in the probability, because we can output the classification tree results in two ways. One is in the probability. So that's the second approach. You see that? I predict the tree on the test set. The type is what? Prob. That's the probability. Then I can do the average. Okay. The first approach is through the majority vote. So the output is on the type is class, not output the probability, but output the class, approved or not approved. So we will do a majority vote. And that also goes back to why I set the B to be a odd number. 201. Why we have a 1? Because to do the majority vote, it's possible, although it's very unlikely, it's possible that we can have an even split if we choose an even number. Let's say if I set the B to be 200, technically it's possible that we can have 100 trees predict as approved, 100 trees predict as not approved, right? So in that case, how do we choose? Of course, we can randomly split, randomly choose one. But if I choose 201, that avoid this situation. Okay, so that's the. Okay, so after running the for loop, this is a for loop for I from 1 to 201. Okay, so after running this for loop, then we will have the bag vote and the bag prob. So you can see the bag vote, that's based on the majority vote. I use the median. Why? Because for the class, I can just use the median. That's the, if we have a majority vote, the median will be the majority vote one. Okay, so that's the median is the majority vote, and the mean, that's for the average of the probability. Then I will, for the probability, I will just use 0.5 as a threshold. If the probability of approve is greater than 0.5, then we will just approve it. Then we'll predict as approve. If it's less than 0.5, not approve, right? So then I will just do the tables and then show the results. So you can see here for the majority vote and the average of the probability, it's 0.125, 0.12, which is either equals to the best tree or slightly better than the best tree. And you may questioning, well, the improvement of bagging is not that much, is not that impressive. Yeah, this is a very small data set. And also the result and the number of variables is not that many. So this is considered to be a quite small data set. So you didn't see much benefit, okay? Although we can see a little bit, but not much, okay? Because we have few, not too many predictors, okay? So if we have relatively large number of predictors, and if the sample size increases, and then you will see the benefit of using the bagging much more than what we observed here, okay? But this is an illustration that shows the bagging trees. You can do it through this, okay? And also, we can also show the results, not just through the misclassification rate. And we can have another approach. So there are actually many ways to quantify the prediction performance, okay, besides the misclassification error. So right now I will talk about another one that's also very popularly used, especially in the imbalanced case, okay? So people likes to use the ROC curve and the AUC scores to quantify the performance, okay? So, so what is the ROC curve? So ROC curve is the receiver operating characteristics curve, okay? So ROC curve, so this is a slide, I will post it in the Moodle right after class. So I will quickly explain what is ROC curve and what is AUC scores. So suppose if we wish to know if the expression level of a gene in a tumor can predict patient have a recurrence of their cancer or not. Okay, so the high expression means high probability of recurrence. So here, the gene expression level, let's say if this is the distribution for the no cancer patients, this is the distribution for the gene expression level for the cancer patients. Okay, and then you want to classify, set a threshold that can classify the patient will have a cancer or not have a cancer based on the gene expression levels. So where should we put the threshold? Very easy, right? We can just put a threshold here. Why? Because these two distributions are very well separated. There's no overlap. So very easy, just set a cutoff here. And we will use that cutoff. So if the gene expression level is greater than the threshold, we predict as cancer. Below, we predict as no cancer, right? Very easy to do that. But what if we have here? If there's an overlap, what should we do? So if there's an overlap, right? So here, this is the distribution for the no cancer patient. This is the distribution for the cancer patient. Okay, there's an overlap, right? So here, if I draw the threshold here, okay, so this threshold, is that good or not? This will have lots of what? So this will have lots of false negative patients. Okay, so what does that mean? We have lots of false negative patients. So here, if we set the threshold here, tell me what is the classification rule? If above the threshold, we should predict as what? If we, for this above the threshold, we should predict as cancer or no cancer? Cancer, right? So above the threshold, we always call it positive, right? So positive is above the threshold, okay? So if that is the case, you see the false positive is very few. Why? Because for the false positive means it's no cancer patient, but it's still above the threshold. So that only counts that many. So very few false positives, right? That's easy to see. But what about false negative? What is negative? Negative means for those subjects that have the expression level below the threshold. But don't forget that we have this big proportion, which about half of the cancer patients are below that threshold. So that causes lots of what? We call it false negative, right? So there's a problem, right? If we do the threshold here, okay? False negative is low, but false positive is high. Oh, I'm sorry, false positive is low, false negative is high, okay? But let's set the threshold here. It's reversed. Why? In that way, the false positive will be a lot because we have so many patients that has no cancer actually above the threshold. So, but false negative will be low. So you can see when we have a low threshold, when the threshold level is low, the false positive will be a lot, but false negative will be low. But when we have a high threshold, false positive will be low, but false negative will be high. Is that right? So if you understand that, okay, then this is the notation for the conditional probability. Okay, so what is a a so the this is the probability that is the it's a conditional probability for given the patients have cancer, the test result is positive. So the probability of having a positive test results given the patient has cancer. And I can write it in the short way is the probability of T plus given D plus. So disease positive, and so that means this is a cancer patient, but the probability of having a positive test results given the patient has a disease, has a cancer. Okay, and this is the notation for this. So then the false, so what is the false positive rate? False positive rate is, before that, let's talk about the sensitivity. So sensitivity is the probability of the test is positive given the patient has disease. Specificity is the probability of having the negative test results given the patient does not have disease. Okay, so this one is sensitivity. Okay, and this is specificity. Okay, so sensitivity is to find out all the disease. Okay, so if sensitivity is 1, what does that mean? That means all the patients that have disease, they have the positive test results. And the specificity is to find only those disease. So that means all the patients that have no disease have the negative test results. That's the specificity. Okay? So sensitivity and specificity depends on how well the test separates the two groups. It actually depends on the threshold. If the threshold changes, the sensitivity and the specificity changes. Right? Okay? So here, let's see if we have a well-separated case. Then we have a good sensitivity and a good specificity. So that both of them are equals to 1. Right? So if we set the threshold here and two distributions are well separated, so the sensitivity is this one. So given all the patients have disease, which are these groups, the probability of having the positive test results is 100%. So the sensitivity is 1. You see that? And similarly, the specificity is among all the patients that have no disease. The probability of having the negative test results also 100%. Okay? So if we have an overlap, then if we have a high threshold, set the threshold high, then you can see we have a good specificity. Why? Because specificity is the probability of having the negative test result among those patients have no disease. So you can see the proportion of having negative test results among those non-cancer patients is the specificity. And this is very high, is about 80%, right? 80% is a good specificity, okay? And but for the sensitivity is low. Sensitivity is the probability of having the test is positive given the patients have disease. So here the sensitivity is about 0.5. So that is pretty poor. Okay, so now you can see that connects with the false positive and false negative. So what is specificity? Specificity is this one. So the false positive rate is what? That's the 1 minus the specificity. That is the false positive rate. Why? Because here the specificity is this proportion. I would say about 0.8. So then the false positive rate is what? Is just 1 minus 0.8. That's 0.2. So that's the false positive rate, because these are the proportions are false positive. They are positive tests, but they are non-cancer. So it's 0.2, right? And here for the false negative rate is about 0.5. That's very high. Why? Because among these cancer patients, we have those about 50% of them are negative test. So that's the false positive. So that equals to 1 minus the sensitivity. So that's the false negative. Okay? So that's the for the high threshold. For the high threshold, good specificity, but poor sensitivity. Okay? But when we lower the threshold, okay, this is high threshold. When we move the threshold to maybe somewhere here, the results will reverse. So when we lower the threshold, you can see now we have a poor specificity because we have many false positive results. So the specificity is about 0.5. Okay, but for the sensitivity, it's pretty high. It's 0.8. And false negative rates is low, is about 0.2. Okay, so you can see the sensitivity, specificity, false positive, false negative, these are all depends on the threshold. And also depends on what? Depends on the distribution for these two groups. If it's well separated, we don't have to worry about that. So we have a perfect threshold, can make both equals to 1. But when we have an overlap, the threshold really matters a lot, right? Okay, so the ROC curve. So what is ROC curve? ROC curve is to plot the sensitivity against 1 minus specificity. Okay, so here, if we have such case, then the ROC curve is what? Then the ROC curve is directly from to the, so it will be start from here, go to that corner, and go to that. So it's a perfect square. It's a perfect square. Why? Because we have a very well separated two distributions, right? So we can just set the threshold here. We have 1 and 1. Okay, so we set it here when the sensitivity is 1. That means what? We reached here. But when the specificity is 1, 1 minus specificity is what? Is 0. Then we got this corner. So that's why we have this corner. It's 1 minus specificity. Okay, so it's here for the 1 minus specificity, and the sensitivity is 1. And then go to the here. So we have a perfect square. Okay, and what is the area under this ROC curve? It's equals to 1. It's equals to 1. And what is the maximum area under the ROC curve? It's always 1, right? The maximum one is 1. Okay, so that's the perfect case. And by the way, sensitivity, 1 minus specificity, they are all within 0 and 1. That's obvious, right? It's a probability. Okay, so that's why it's between 0 and 1. Okay, but when we have this case, okay, let's look at for the high threshold case. For the high threshold case, remember we have a good specificity. So good specificity means the specificity is large. But what about 1 minus specificity? That will be small. So for the high threshold, the 1 minus specificity is low. Okay, so here, okay, let's say if this is here is 0.1, let's say 0.1. Okay, so we put 0.1 here, and then the sensitivity is poor, is 0.5. Okay, so 0.5 is here, 0.1 is here. So we are about here, right? So this is the 0.1, comma 0.5. So that's the coordinate for this, right? And then, okay, so that's for the high threshold here. But what about we use the medium threshold? So we reduce the threshold a little bit to here. So we will have the medium specificity, medium sensitivity. So we will have the point is here. So the specificity will decrease. So that makes the 1 minus specificity increase a little. But the sensitivity goes higher. So we go to here. So we moved from here to here, right? Okay, then if we further reduce the threshold to here, then we will have a low specificity, right? So the low specificity, that means the 1 minus specificity will be pretty high. So it's here. And the sensitivity is very good. So we further increase the sensitivity, but the specificity decreased. Remember, specificity decreased, that means 1 minus specificity also increased. Is that clear? So we move from here to here by reducing the threshold, by reducing the threshold. Okay, after we reduce the threshold, the points will go from here to here. Okay. Okay, when we have the extremely low threshold, let's say we have all these subjects, no matter cancer or not, they are all positive. Then we will reach this point. Why? Why this point? Because when we have that, there's no specificity. Why? Because there's no negative patients. There's no negative test results. So the specificity is 0. When the specificity is 0, 1 minus specificity is 1. So that's why we reach here. And the sensitivity also is 1 because we have all the positive. Of course, if the patient has a cancer, the test always positive. So we will have a 1, 1 here. So you can see when we reduce the threshold from the highest, if it's highest, it will be here. Why? Because the specificity is perfect, is 1. Then 1 minus specificity is 0. Okay, but the sensitivity is 0. So will goes here and here until here. So that is the direction when we reduce the threshold. When we reduce the threshold. So when we reduce the threshold, it will goes from the lower left corner and move to the higher upper right corner, upper right corner. Is that right? So that's the trend when we reduce the threshold. Okay. So this is a typical ROC curve. So why we need to have an ROC curve? The reason is that the ROC curve does not depend on the threshold. Is that right? Because for each point, it depends on the threshold. But the whole curve, if we look at the whole curve, that is a spectrum that covers from the extremely low threshold to extremely high threshold. So the curve itself covers all the possible threshold. You see that can show a general performance for the classifier over a large spectrum of the threshold. Okay, and then, but you may ask, how can we quantify that? You cannot just give me a curve. How do we compare different curves? Yeah, a simple way is to find out the area under the curve. So the area under the curve. Why? Because you can see if the classifier is a very strong classifier, the curve, the ROC curve will point towards that direction. Remember, if we have a perfect separation, it will be a perfect square, right? If we have a random guess, do you know what is the ROC curve looks like? If it's a random guess, it will be exactly on this diagonal. Okay? Why? Because if it's a random guess, what will the sensitivity be? What will be the specificity? Okay, think about that. So that will just follow exactly on this XY line. So that's the random guess line. Okay, so from random guess to the perfect, it's that. So when the classifier becomes more and more powerful, more and more accurate, the curve will push towards the upper left corner. So that's why using the AUC score, area under the curve will be a very good number to quantify how good the model in terms of the prediction performance. And that number does not depend on a single threshold. It's an area under the curve that covers all the possible values of the threshold. Okay, so that's the ROC curve and AUC scores. Okay, so the poor test will have the ROC area near 0.5. That's a random guess. A good test will be close to 1. Okay, but 1 is the perfect. It cannot go beyond 1. Okay, okay. So in practice, you may ask, is there a gold standard to say this classifier is good or not? Usually people use 0.8. If it's below 0.8, that's if it's below 0.8 and but above 0.6, that's like a mediocre classifier. It's okay, but not that impressive. But if it's 0.8 to 0.9, that will be a good classifier. If it's 0.9 to 1, that will be a very powerful classifier. If it's 1, that's a perfect classifier. Okay? And the good thing for this is that is very useful for the imbalanced case. If it's imbalanced, that means, let's say we have 2 classes. If class 1 only consists of 0.05, 5%. If for class 2, it contains 95% of the samples. So 5% of the samples goes class 1, 95% of samples goes class 2. So if you do a classification, a very naive classifier just predict all the samples as class 2. In that way, the misclassification rate is 0.5, very small. However, the AUC score will be what? Will be 0.5. So that's why AUC score can be a much better evaluator for the imbalanced case, while the misclassification rate can be not much informative in the imbalanced situation. Okay, so that's the ROC curve and AUC score. So in the data mining machine learning, more and more researchers use the ROC curve, AUC scores, okay, to evaluate the model performance. So here there are lots of library in R can calculate the AUC score and plot the ROC curve. So here I'm just using a library called AUC, and I can so here I calculate the AUC scores. You can see, although these from the misclassification rate, it seems to us that bagging doesn't give us much benefit. It does not improve the prediction performance a lot on the test set, right? Compared to here, the best one. I mean, okay. But if we look at the ROC curve and AUC scores, okay, so this red one is the best single tree, which is a stump. You can see the AUC score is about 0.879. So that's the area under the curve. But the bagging 100 trees gives 0.936. So that is much better than this in terms of the AUC score. Okay, so that is uh, for measuring the predictions. Okay, now besides the predictions, as I said, we have two general purpose, right? One is prediction, one is interpretation. Interpretation also very important. And for those ensemble methods, one of the biggest criticism for these ensemble methods is what? Is you cannot have an easy interpretation because the ensemble model based on hundreds of trees, hundreds of models. There's not simple way to just visualize the model like a single tree. If we can just have one single tree, we can see the model. But if we have so many trees, how can we do the interpretations, right? So what are the interpretations? Think about that. If we have a data set, you apply the bagging trees. So in terms of interpretation, I would say the most important or most relevant questions in terms of the interpretation is like, what are the most important variables? Is that right? So how can we measure the importance of a variable using trees? Okay, so let's see that. So here, we can look at those splits. What are the variables used in the trees, right? So you can see if we just look at this single tree, okay, for this single tree, A8, that has been used in this tree, right? And then followed by A3 and A9 and so on. So now if we consider all these trees, remember in that ensemble I used 201 trees. If I look at all these 201 trees, let's see what are the variables that has been used in the splitting. Okay, and you may ask, how can I find that variables that are used in the split, right? So for those, here, did I? Let me see. Yeah, so here, in the tree objects, okay, so here I'm showing you the tree objects. There is a fit2 is a tree object. In the fit2, there is a component called splits. Splits is a matrix that shows the number of observations in that split and the number of categories in that split for that splitting variable, okay? And the amount of improvement for that single split. And these two, you don't need. So here, first is we have and these are the variables that used in the split. Okay, so for each tree, we have that splits objects, and we can easily find out what are the variables that we do the splits, right? And also the improvement. Remember, we talked about that last time. Okay, we can easily find out the improvement for a single split. Remember, if we have a regression tree, right? How much improvement for that split? So we can easily see that first, without this split, what is the sum of squares errors? I'm using a regression as an example. And then if we do these splits, now we have two branches. Now we can find out the SSE, sum of squares error from this branch, and sum of squares error from this branch. And that will be the sum of squares errors after doing that split. And usually this is much smaller than the SSE. So SSE without splitting will be much bigger than this. And that difference is the improvement by this split. Okay, that's for the regression. But for the classification, instead of using sum of square error, we can use what? We can use cross entropy or Gini index, right? So this is how we calculate improvement for each split. Okay. So now, if you see these objects, then we can easily find out what are the variables used. Okay. So this is these lines are the code in the R that you can easily find what are the variables that used. And I also counted the number of trees that use these variables. So you can see here we have A8 has been used in all the trees because we have 201 trees. And also we found another variable A5 used in almost all the trees. Right? So it seems to us that these trees must be very important variables. Right? But just using the frequency, that may not have a good reflection of how important it is. Because we also need to use the importance that, or we also need to use the improvement to make a better estimation of the importance, right? So here, this is the code that I calculate the importance or through the improvement for each variable. So I take the summation of all the splits that from a particular variable, and then added all the improvement for that variable, and use that as a numeric measure of the importance for that variable. Okay, for example, let's see for the A8, it just used once in that tree. So the contribution for that A8 is 120, right? And for the A13, it has been used twice in the splits. But the improvement is what? 2.28 and 4.44. So what is the contribution of A13 in, in this particular tree? It will be just 2.28, then what? Plus 4.44. Is that right? So that will be the contribution for the A13. And this will be the A8. Okay? So these are the numeric measure of contribution, and I would say the importance for these variables. Okay? But what if like some variable that is not used, like A2? If A2 is not used in this tree, then the contribution will be 0. Does that make sense? Okay, so to do that, I use this code. Okay, so you can see after running through all these 201 trees, so I added all the importance for all from all these 201 trees. Okay, so you can see these are the importance for all the 14 predictors. Okay, look at these numbers. So this is for the so we have here the 8.5 and A8, right? So let's look at, so here for the A5, that's 1, 2, 3, 4. So that's A5. And that's A8. So although A5 appeared in 199 trees, almost all the trees use A5, and this A8 appeared in all the trees. But look at the improvement, summation of the improvement. A8 is much, much more important than A5. So that means what is the most important variable? It's A8. There's no questioning on that. So A8 is the dominant, most important variable in this model, followed by the 8.5. But also A9 is quite close to the A5 in terms of the improvement, right? So this just gives you an idea that how we can find out the importance through the improvement, okay? Okay, now let's go to the crime rate example. This is a regression case. For the regression, this data is from the 1990s U.S. Census, and we have about 2,000 rows and 128 variables. But some of the variables are not, the first 5 variables are not used for the prediction purpose, so I just removed that. And the next 122 variables are the predictor variables. And the last one is the response. Okay, so the response is the total number of violent crime per 100K population. Okay, so we want to estimate the crime rate using these 122 predictors. It's a regression problem, right? Okay, so I will also post this data to the Moodle after class, and you can play with that. And this is the first few. So here we have some missing values. So I calculate the proportion of missing value for each variables. Okay, and you can see very interesting. This is the, like all these variables has no missing value. But starting from the 102 variables, you can see the proportion of missing value is the same, exactly the same. 84% missing, 84% missing until here. And then starting from here, 84% missing, and this one 84% missing. So if then I go to the details for the data set, I found all these missing values. Why they have exactly the same proportion? Because they are missing on the same subjects. Okay, so since the missing proportion is very large, so I just eliminate these variables that has missing values. So I just removed x1, 102 through all the variables has 84% missing values. Okay, so I remove these. Now I only have 100 variables, has no missing value. Okay, so this is the cleaning of the data set. So after cleaning the data set, then I randomly split the data as 1,000 as training, and the rest of the almost 1,000 as a test sample. Okay, then I fit a tree, regression tree, and using the same way to do the cross validation, and then find out what is the best tree, best single tree, just one tree. Okay, so best single tree to do the classification, and you can see to do the regression, you can see what's the best one. The best one is I think it's this one. If I look correct, the best one is this one. So the mean squared error is 0.1521 or 12. Okay, so that's probably, wait a minute, it's here, 0.1505. It's this one. Okay, so this is the lowest. That's the best we can achieve for a single tree. Okay, so now I use bootstrapping. Now this time I'm just using 100 trees. Okay, there's no even split. Okay, this is not a classification, just a regression. 100 trees and just do the average. The bootstrapping is still using the R multi-norm, and then just do the average. You can see the mean squared error is 0.136, which is a substantial improvement compared to this one. If you calculate the relative percentage improvement, that's about 15% improved. Okay, so you can see the benefit of using the bagging in here is about 15%. And then we can find out what is the most important. Okay, so I use the improvement based on the I use the improvement as the quantitative measure to get the importance variables. Okay, so I find out the most important variables are x50, x56, x9, x49, x77. So these are the most important variables. And the next column are showing the improvement, average improvement. So you can see the X50 has the largest average improvement, and followed by the X56 and so on. So these are the leading 5 most important. Okay, so after that, what is the second question? If we find out the most important variables in the model, so what's the next question? The next question is we want to see what is the effect for this most important variable in the model, right? Are they have a linear effect on the model or nonlinear effect on the model? Are they having a positive or negative or quadratic effect? Something like that, right? We want to know how does this important variable impact the response, right? So let's see how we can do that. And by the way, there are package can do that. And the reason I want to use I want to show just write my own code is just to give you a better understanding. So you don't have to write this by yourself. There are lots of package in R can do that for you. But if you wrote this line by yourself, and I can tell you, I can guarantee that you will have a much better and much deeper understanding of, oh, this is the importance of a variable. Oh, this is how we find out what is the effect on that variable on the response. Okay, so what we do here, I'm just showing you here, since x50 is the most important, let's see what is, and x56 is the second. Let's see how we can get these two variables, find out their effects. Okay, so what we do is, the idea is very simple. Remember, when we interpret the multiple linear regression, like here, let's say y equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon. Okay, so this is a very simple multiple linear regression, two variables. So how can we interpret the impact on the x2, impact of x2 on the y? We can say, given the x1 is fixed, and if we have 1 unit increase in the x2, the y will increase by beta units. Is that right? That's like a standard interpretation for the effect of x2 on the response y. But don't forget that what's the first part? given the x1 is fixed, when we increase 1 unit in x1 or x2, then the y on the average will increase by beta 2 units. So don't forget that given. Okay, so just like that, we need to, if we want to estimate the impact on the x50, what should we do for the rest of the variable? We should fix at a certain amount. Does that make sense? Right? If other variable changes, there's no way we can estimate x50's effect, right? So the point is, so the tricky point is, how should we fix the other variables, right? It's not an easy question. It's not. I will show you an example maybe later, okay? So if here I'm fixing at the median, so here I'm fixing at the median. So look, I apply using the apply function and get the median for all the variables. Okay, so then I fixed all the other variables at the median. Okay, then when I look at the x50's effects, what I do is I change the x50 from the median to what? To a fine grid of x50 from the minimum value to the maximum value. Is that clear? So that means I fix all the, when I explore the effect of x50, I fix all the other variables, including x56, to the median, to its own median. And then I set the x50 from the minimum value in the data to the maximum on a fine grid. How fine? I set 101 steps. Okay, so then I do the prediction on this data, on this artificial data. Remember, in this artificial data, all the other variables are fixed at the median. The only same changes is what? Is x50. Is that right? From the minimum to the maximum. Now, the predicted value from that model also changes. Is that right? And can we say that the change of the output is entirely based on the change on the x50? Is that right? And that's how we estimate the x50's effect. So you can see idea is very simple. Okay, now how to find out the effect on the 56? Exactly the same. Set all the other variables at the median. This one changes from minimum to the maximum on a fine grid. And then to see that. So now you can see this is the effect on the x50. This is the effect of x56 on the response. So you can see they are entirely different. So x50, when the x50 increases, you can see the value of the response actually what? Decreases. But x56 is exactly the opposite. It increases. Okay? And if you look at the top axis, I put some tick marks on the top axis. That shows the terciles. That shows the decile. So the first one is the 10 percentile. Okay, and the second one is 20 percentile, 30 percentile until 90 percentile. So deciles of the x50. So that basically tells us the distribution of the x50 in the real data. So why I show that? The reason I show these deciles from 10 percentile to the 90 percentile is to show the majority of the x50 falls into about that range, within this range to this range. So we should focus on this range. Is that clear? So the main body of the x50 is within that range. So you can see there is a decreasing trend. And you can see we have a flat tail on both sides. These are artificial. Why? Because remember, for the trees, we use constant in the regression. So these flat are artificial. And these are the sparse regions. We don't have much data points. So that's why it's a flat. Okay. Similarly, for the X56, we should focus on these regions. And these are artificial flat tails. And even for this flat region, I would say you have to interpret, be very cautiously. That may be due to we don't have much data points within that range. Okay, so anyway, but we can have a general trend is increasing for the X50, decreasing for the X50. Okay, so that gives you a very good example that how we can interpret, still do the interpretation for the ensemble method. Okay, any questions? And we will talk about that more when we reach the random forest. Okay, if you don't have any question, let's stop here. And don't forget to each group send me an email, have a description of your data sets and your group member's name and also the the methods that you plan to apply on the children data set. Okay, so let's stop here.